Hello, ESC523. This video will give you an overview on Xmon qubits, which is a superconducting charge qubit that's pretty important and relevant for error correcting circuits. But before going into the details of the Xmon, I just wanted to pull up DiVincenzo's criteria for a universal quantum computer, so you can keep these in mind throughout the presentation. Superconducting qubits are definitely viewed as attractive architectures because of their scalability, as well as the fact that we already have tremendous infrastructure to mass produce superconducting substrates. But one of the trade-offs for scalability is that superconducting qubits have had a historical difficulty in obtaining long coherence times. And one of the main design drawbacks is that these architectures need to operate in the millikelvin regime, which is difficult, but it's not impossible to engineer. So to provide a historical overview on how we got to the Xmon qubit, it starts off in 1925 when Born solved the quantum harmonic oscillator. And so just as in classical mechanics where we can map the solution to the mechanical simple harmonic oscillator to the classical LC circuit, we can do the same thing in the quantum regime. So that was done in 1925. Then Sherman came up with the Qubit parabox, or the charged qubit, in 1997, which was verified in 2001. And then the Koch group came out with the Xmon, which is a variation of the charged qubit, in 2007. And then Barron's and his group in 2013 came up with the Xmon design. To understand the Xmon qubit, it's really important to fully understand its predecessor, the Xmon qubit. And to understand the Xmon qubit, let's do a brief overview of the charged qubit. So remember, in the charged qubit, or the Qubit parabox, which we treated as a nonlinear quantum oscillator, there was a sweet spot where the qubit eigenenergies are insensitive to offset charge noise. And this control parameter was a function of the offset charge, which we had to set to 1/2. This becomes a problem for effectively performing quantum control over the qubit because we'd ideally like to minimize noise error fluctuation in our design. The Xmon solves this charge sensitivity problem by adding additional capacitors into the circuit in order to increase the ratio of EJ to EC, which you can see in the equation on the left as well as in the circuit diagram on the right relative to the Qubit parabox. Notice that as your EJ to EC ratio increases, the energy difference between the first two energy states of the qubit becomes increasingly independent of the charge noise or order parameter. This makes the qubit transition frequency extremely stable with respect to offset charge. As always in quantum engineering, there's a trade-off. In this case, that trade-off is the reduction of anharmicity between the two qubit states. Notice on the last graph where the ratio is 50, that difference between the two states is almost zero. Remember, if the energy transitions are linear, or the energy difference was zero, we wouldn't be able to resolve the two different quantum states, and that's why anharmicity is important to consider in qubit architectures. The Xmon qubit is really a Xmon qubit with a couple of upgraded features. So you might see in the literature nowadays that Xmon qubits being referred to as Xmons, and that's just because they're extremely similar, FYI. But so originally the Xmon qubits were two separate differential circuits, as seen on the left-hand side. They lived on the same chip, but they didn't share a common ground reference to couple them. The way to couple two Xmon qubits was through a bus resonator that relied on photonic coupling within an optical cavity. This method worked, however, becomes superfluous and bulky if you're trying to fabricate for scale. So the Xmon qubit gets its name because of its crossbar structure. The primary innovation of the Xmon is really in the scalability and very easily tunable design. So instead of coupling through an optical resonator, it couples with other Xmon qubits via direct capacitors sharing a common ground. So the XY control, readout, and coupling mechanism, the bus, are all mediated by capacitors. The most important thing here is that the Xmon, the three-arm capacitor coupling method, enables fast control and a scalable fabrication process that sets the stage for the realization of linear arrays of Xmon qubit processors. There are four main components of the Xmon qubit: the XY control, the Z control, and the two coplanar waveguide capacitors, one for readout and one mediate coupling between other qubits. Three of the connections are easily made with coupling capacitors, which provides a significant advantage for individually tuning and optimizing each coupling arm in the context of microfabrication. And then modeling the system also comes easier without having to fully invoke quantum optical methods required in Xmon qubit coupling. So the XY control drive is responsible for exciting the qubit state. It's mediated by a coupling capacitor. Note that it's got fast control, so it excites the qubit in 10 nanoseconds, which hardly has any effect on our T1 coherence times because it's on the order of milliseconds. So the Z control is responsible for tuning the qubit frequency. It's composed of a nonlinear squid with a high inductance and operates at 25 nanosecond control time. So this is sort of similar to the X control variable used in the Cooper pair box example in the slides. But then also it plays an important role in increasing our EJ-C ratio to make it higher. The other important components on the north and east arm of the Xmon are the coplanar waveguides, which are thin aluminum wires that connect coupling capacitors to the readout resonator and quantum bus for mediating coupling between other qubits. These waveguides in particular exhibit a high Q of 10 to the 6th for single photon excitations. So in the Barron's experiment, they used aluminum material and identified the transition frequency at 6 gigahertz. They achieved a high EJ-C ratio of 95, which helps eliminate qubit sensitivity to charge noise. They also achieved a single-shot readout fidelity of 70 to 85% with a Q of 10 to the 4th. And the qubit coupling strength was 40 megahertz, and the temperature was conducted at 30 millikelvin. Furthermore, they accomplished a high T1 relaxation time of 44 microseconds and 15 microsecond coherence time. So when comparing different charged superconducting-based architectures, I just want to note that this data comes from the initial paper, as well as the quantum engineering guide to superconducting qubits. So there might be some information that it's outdated, so apologies to any viewers who might be more knowledgeable in the subject of flux and fluxonium qubits and have updated information on the relevant figures of merit. But by looking at the comparison chart, you can see that Xmon currently outperforms other superconducting qubits in terms of coherence times. While this is sort of a crude comparison without the appropriate due diligence involving a cross-industry deep analysis, the relevant trade-offs of designing implements are shown on the right side relative to the Xmon. So in general, one of the greatest advantages of the Xmon architecture is its tunability as well as its scalability, and that stems from the coupling capacitor architecture on the arms. The Xmon solved a lot of engineering problems associated with the charged qubit and transmon qubit through the crossbar architecture, and the trade-off in comparison to the flux and fluxonium qubits is that the flux qubits are able to provide much greater anharmicity between states. But the price you have to pay, though, in the flux qubit case is added complexity in circuit design, which may potentially pose implementation problems when trying to scale. In addition, fluxonium qubits have been traditionally difficult to tune. So this paper had relatively immediate impacts, as the same group were able to develop a 5-qubit quantum processor out of the Xmon coupling design a year later, in 2014. The linear array of Xmon qubits is suited for surface code error corrections, which is basically a protocol to not only determine that an error had occurred, but also detect what type of error occurred. I'm not an expert on the subject, but you can sort of think about multiple gate operations on an integral qubit. They could have degenerate eigenvalues corresponding to non-equivalent eigenstates. So the important thing you would want to know is which eigenstate is this qubit actually in, and given some input and potential error between gate operations. And that's a very rough idea behind surface code error correction, and this Xmon architecture satisfies the criteria by achieving high fidelities of 99.92% for single gate and 99.4% for 2-qubit gates. And this is a significant accomplishment given that the threshold fidelity for surface code error correction is 99%. Current state of the art is that Wang's group in 2018 achieved a gate fidelity of 99.8% in an Xmon qubit. They essentially implemented some microwave engineering techniques to mitigate parasitic inductance, which was a suggestion at the end of Barron's 2014 paper. Another one is, while I couldn't gain access to this research report, there was an abstract containing a 10-qubit Xmon architecture from the Su group in 2019. I wish I could give you more details about how that was actually done or for what purpose, but unfortunately the body of the report wasn't available. And one of the more interesting developments was an apparent demonstration of a violation of Bell's inequality using superconducting qubits in 2019. They coupled two Xmon qubits through a 78 centimeter transmission line, and apparently achieved a violation of inequality, but I'm somewhat skeptical. If true, though, this places superconducting qubit architectures on the map for quantum communication and cryptographic protocols. But that being said, it was rather nebulous whether they in fact closed the locality loophole and satisfying the Einstein locality conditions. And I'll link the paper for the viewer to decide because I'm unclear. So for the Xmon single qubit, the authors of the initial paper alluded to the idea of experimenting with additional arms that can increase the possible couplings a single qubit can have. That might be interesting. I'm not quite sure exactly where you probably could generate some different error correction algorithms through that way. But moreover, they acknowledged that they hadn't reached the T2, T1 limit for coherence times and intend to investigate new materials like titanium, nitrogen, because of reported higher coherence times from other literature. As far as it comes to the Xmon-based surface code error correction processor, the authors cited the total distribution of error corrections as seen on the right. So decoherence can be reduced through enhanced materials and optimized fabrication. So the control error was caused by stray inductance, so that was solved by Wang in 2018 through microwave techniques. And then the state leakage apparently can just be suppressed by slightly increasing the gate time. So ultimately the goal would be to continually increase the qubit capacity of this Xmon architecture. It seems scalable, and the linear array model would be robust and could generate high-powered error correcting circuits going down in the future. Thanks for listening to my presentation on Xmon qubits. In these sort of uncharted territories, thought I'd give you guys a little bit of inspiration. Stay safe, stay healthy, and hope to see you in the fall.